No, it's good. Right. Go on. Oh, that's good. Yeah.
Okay, can you hear me? Okay. So let me welcome all of you to the second talk by Dr. Sakurai from Okinawa Institute for Science and Technology. I mean, I had introduced him in his first lecture. So I'll just say that both during his doctoral and postdoctoral work, he has done groundbreaking work on quantum machine learning. And he will talk about some of that today. Reservoir computing utilizing quantum dynamics. But he has also worked on other aspects of quantum machine learning. In particular, he has worked with Pan's group in China, where they have used a different kind of quantum machine learning and have combined it with quantum sensing to study quantum many-body states. So with these few words, so let me invite Dr. Sakurai to give his talk.
Okay. Thank you. Okay. Yeah, thank you, Professor Duff, for nice introductions. Good morning, everyone. And actually, it's my first time I gave the talk in the morning. Generally, my talk is put it in the afternoon. That's why I cannot enjoy the lunch. But today I will enjoy the lunch. Okay. Anyway, today I would like to talk about utilizing the quantum dynamics, renewable dynamics for reservoir computing, or I can say for quantum machine learning. So this is the outline of this talk. It's really simple. So first, I will talk about introductions, about the current. Okay. And then I will talk about our model, quantum extreme reservoir computing, and I will show that a few our recent results. Now, recently, it has become possible to realize the actual quantum devices having 10 to 100 qubits. But these devices are very noisy. That's why it's called noise intermediate scale quantum devices. And there are so many platforms proposed. For example, superconducting qubit or trapped ions, or maybe silicon and others like a cold atom. At the beginning, people believed that NISQ devices might be used to fault tolerance quantum computer. However, to make a full quantum computer, we need more qubits, and because they need error corrections. And at the current level, it's still challenging. So, however, the NISQ devices has been used and gets a nice result on the simulating the many-body dynamics of quantum systems. For example, as showing here, this is a I think quantum walk using 12 qubit, and this one is a theoretical project, and this is experimental result. And you see that the agreement between experiment and theory is very good. And they also show that it's possible to prepare their own, like by tuning the frequency of driving, it's possible to implement any kind of potentials. And or it has been, NISQ devices has been used to demonstrate or realize a new phase of matter, as I explained in the last talk, like a time crystal. And time crystal actually has been made it or realized in many other platforms, for example, superconductor qubit, trap ions, or NAV centers. And recently, Google showed that submitted a new paper, and in this paper, they say that they made the time crystals using 57 qubit. And this is not experiment, but interestingly, it is known that even the small system around 8 to 12, it's possible to find interesting network structures in the quantum dynamics. So NISQ devices has is a good device to make or realize the complex dynamics of quantum systems. And then can we use these complexity in dynamics to design a new type of quantum computing? And one approach is a neural network, quantum neural network. So what is a neural network? So I would like to roughly, briefly explain what is a neural network or artificial neural network. So roughly say it is a mathematical model inspired by the biological neural network of our brain, like this one. So in our brain, we have a neurons, and these neurons are connected and make a network structures like this. Similarly, in artificial neurons, neural network, we have artificial neurons, sometimes people call nodes, and these are connected to each other and they make a network structures. And first, and it is proposed to understand what is happened inside the brain. But nowadays, neural network are used or applied to machine learning, such as deep learning. Now, in the deep learning, we have an input layer and output layer. The input layer is for use to input the informations. For example, let us consider the image classification as a simple task. And here I'm showing some images. This is this number 5. And we want to get some result from neural network. In this case, we want to get the 5, the number of these images. And to get desired output, we have in machine learning, we need to optimize the network or weight of the network in the training. Now, how many neurons do we need to make to solve the given problem? For example, in our brain, we have 14 billion neurons in the cerebral cortex or in the brain. And actually, it is hard to realize in the classical computer because if we want to realize the same amount of neurons in our brain in the laptop or classical computer, it requires many size and actually it's difficult. But however, it might be possible to replace this part with quantum system because it has a huge Hilbert space. Then some people propose the quantum circuit learning model. They replace this part by quantum systems, and they call this as a quantum neural network. And this is like a circuit. And it's parameterized circuit and having some parameter variables. By tuning these parameters, it's possible to, similar to the original machine learning, it's possible to get the desired output. And to optimize these parameters, generally people use a variational quantum algorithm, so-called a BQA. But the problem of BQA in quantum circuit learning is it's sensitive to the noise effect. And also, it is known that they are Barré-Plateau problem. So I'm not sure how many people are familiar with the Barré-Plateau's problem. So briefly say that the exponentiality of quantum circuits is increased, or if we have good neural network, like it's covered almost all accessible space of unitary of this circuit is almost covered the whole space of unitary space, then the cost function is necessary to optimize the parameters become very flat. And as a result, it's hard to optimize it. So it means that the quantum circuit learning it's hard to perform on NISQ devices. As I said, it's sensitive to noise and their variable problem. Thus, but that to avoid the problem in of quantum circuit learning, the other quantum machine learning approach is proposed, which is called quantum reservoir computing. I think first proposal is this one. Professor Fujii proposed that this type of computing. Actually, there are classical reservoir computing in the classical machine learning, and Professor Fujii expands the idea of classical reservoir computing to the quantum regime. So briefly say it has four layers, input, quantum neural network, and the classical neural network, and output layers. So in the reservoir computing, we use the quantum neural network to create the huge quantum neural networks. And we call this part the quantum reservoir, and we don't touch this part. And optimization is applied to only the classical neural network part, like here. And the original proposal, they tried to use the quantum reservoir computing to solve the temporal data set, like a voice recognitions or video. Because the original, classical reservoir computing, they also proposed to solve the voice recognitions or video. But the problem of the temporal data or reservoir computing is that we have to have some memory effect in the reservoir. But as you know, in the quantum systems, we have to measure at some point. And this measurement is, after the measurement, the state is collapsed or projected to some state. We cannot get the memory. We cannot. So I think it's impossible to keep the memories, used as memories generally. That's why we think that, okay, we use quantum reservoir computing to solve the statistic input, like image or image classification, like a task. And the fundamental question is, how much complexity is needed? And can it perform a task with huge input, such as images? Now, this is a model of our quantum reservoir. We call it the quantum extreme reservoir computing. So it has 5 layers. So we have encoder part because our input is a classical data, like 2D samples or images, and these are classical information. So we have to have an encoder which converts classical information into the quantum information, like a state. And this state is evaluated, it's mapped to the final state by quantum reservoir. So this is it's called quantum hidden layer or maybe reservoir. And after that, we have to measure it to convert the quantum information into classical. And this we get classical information at the M layer. And this information is then sent to the classical neural network and optimize it. And we get some classical output. Now, let me briefly explain each part. But first, I would like to explain the more details of this part, encoder part. As an example, let us consider simplest case, 2 inputs, 2D samples, and these dots represent the data. Each data has 2 variables. And for example, if we have a qubit as a quantum systems, we want to use it as a reservoir. And how to encode these information into qubit? It's easy. Because a single qubit state can be represented by two angles, like this one, or you can use, let's assume the block sphere, and there are two angles. So by map to these variables to the angles, we can encode the information into the block sphere, or maybe single qubit state. Now, I would like to talk about the reservoir part. So in my talk, I would like to show you the two results of two different reservoirs. So first reservoir is a 2D discrete time crystal model, like a natural dynamics, natural quantum dynamics. And I have already explained it in the Monday of this week. But to remind you what's the time crystal, I would like to briefly explain. So this is the time periodic systems, and this is a Hamiltonian over the discrete time crystal, and it has two parts. And the first Hamiltonian represents a flip of spins, the spin flip with error. And second part represents the many-body interaction between qubits. And here I'm assuming that the interaction length is long range. The why we choose 2T DTC as a reservoir is because it is easily performed on the quantum NISQ devices, as I said in the beginning, introductions. Because it has been demonstrated in different platform of NISQ devices like a superconductor qubit, trap ions. And it is also known that the complex dynamics can be created by this model, dynamical phase transition and instead scale-free network. Okay, let's briefly explain what is that. Okay, here we have epsilons, and as I explained in the previous talk, by changing the epsilon rotational error, it's possible to realize two different dynamics. When epsilon is very small, it shows a very regular dynamic like this one, and we call this a DTC phase. Oh, sorry. On the other hand, when epsilon is large, over the critical point, it shows the very chaotic dynamics. And it's sometimes called mated DTC phase, or MBL phase, or maybe thermal phase. The interesting point, why, is that at the critical point, it is known that they show some network structure called a scale-free network. This part is very also interesting point of DTC. Now, the second case two, we also consider the reservoir, which is a randomly realized or samples from the 4 unitary space with hard measure. Like suppose we have a unitary space, 4 unitary space like this one, and throw the uniform die and create one unitary, and we use this as a reservoir. Because how random unitary is known as because it is not considered to be complex enough in the previous work. But the problem is it's hard to realize on NISQ devices. For example, to demonstrate the Hall measure, the random unitary, to make Hall random unitaries, we need many rotation gate and two qubit gates. Like I think everyone knows the paper by Google in 2019. They show that the quantum supremacy paper, and they demonstrated that similar to this type, they create some circuit to generate a random unitary, but they have many gates. Now, the final part. So we have reservoir and we have input, and the input state is converted to the final, the map to the final state by reservoir. Then we need to measure it. So in the measurement part, we measured the quantum state with computational basis. And because of the stochastic probabilistic process of the measurement, we get a bit string among these. There are 2 to the power of n possibilities. So we get sometimes 0000 or sometimes 0001 or 1111. So they don't have informations, or we cannot get any informations from only the single binaries. That's why to get informations from reservoir, we need a many shot and count the number of bit strings and calculate the probability distribution. Now we can get some information from these of reservoirs. We input this distribution into the classifier. And in our model, we want to use the simplest classical classifier. And that's why we use a single layer perceptron. So it has a M layer or maybe input layer for, I can call it as input layer for classical classifier or single perceptron model. And we have output, and we have one neural network or network, a network. And we optimize this part only using gradient descent. Now, before I showing our result, I would like to brief note one point. So, single perceptron model does not, without quantum reservoir, cannot solve, can solve the linear separable problem, but not nonlinear one. For example, this is a linear separable problem because we can draw the line here, then we can separate the 2 regions like blue and red. On the other hand, this one is known as a nonlinear Gauss separable problem. So single perceptron model cannot solve this type of problem because it cannot distinguish by with single lines, right? But so we expect that quantum reservoir gives the SPM the power to solve the nonlinear problem. Now, let us check this point. So this is a demonstration of a QERC with a singlest example. So we consider that this type of task. So these cross dots represent the training data. And this is called isotopic Gaussian samples. And these tiles is a result predicted by QERC, result of QERC. Now this represents the time or period of time reservoir. For example, at the initial time, it means that there's no dynamics. It can, as I said, it cannot solve this type of problem. Isotopic Gaussian problem is not solved by QERC because time is 0 means there is no dynamic. Now let me see. Sorry. Okay, this is a PDF. Sorry, I put the document. Movie here. Sorry, but unfortunately it doesn't work. Sorry. Okay, at the 30 period case, because enough complexity is generated in the reservoir, now you see that it can solve. It means that at the time increases, the DTC get enough complexity to solve the isotopic Gaussian sample classification problem. So it indicates that QRC perform it as a powerful as other QCL and QRC, because this type of problem is also used as a benchmark in the other NISQ applications such as quantum reservoirs and quantum circuit running. But this problem is too simple to see the computational power of reservoir, because any reservoir quantum reservoir, any unitaries reservoirs can solve this type of problem because it is very simple. So thus, to understand how much complexity needed for QRC, or can it perform classical tasks with numerical input such images? To answer these questions, we need to consider the more complex task. For example,
data, the periodic drive that you spoke about, that allows you to classify the data that you have.
Used to classify. What do you mean? So used to classify?
Periodic drive that you spoke about.
Yeah, is this is the dynamics. We use the TTC model. It's a time periodic systems. We put this Hamiltonian in the quantum reservoir and we wait 30 period.
But you don't do any optimization of the parameters here at all.
Sorry. We optimize the classical part only.
No, I'm just trying to understand the goal or the role of the dynamics there. So how is that helping you is what I'm trying to understand.
I see.
So it's classifying the input data. You've sort of encoded your amplitudes. The input information is encoded in as amplitudes, right? Amplitudes of the space.
Yes, yes.
And that undergoes some dynamics. And then you're measuring the state after a certain time period. And then you're trying to use a classical classifier to separate, to separate out the data.
Yes.
So what is the intuition behind choosing that particular kind of a drive? Or in other words, that's what I'm trying to ask. So the periodic drive that you had, the ZZX kind of an evolution?
It's a good question. Thank you.
Yeah. How is that helping you to separate out your information or segregate your data?
First of all, you have to, sorry, what's a good way to answer this? Okay, let's be back to here. We encode two variables into the single state. So now, input size, original input size of 2D sample is 2. Because x1, xy1. Now it inputted single qubit, but this it make a network, right?
Right.
Spin network or qubit. And using dynamics, the information is separated, spread over the spin network. Now its dimension become larger than its original input. And in machine learning, it is known that by putting the huge layers in between the input and output, it helps the neural network to they get power to solve. It seems like the kernel method. Have you heard the kernel method? Okay.
So that I think what she's trying.
High dimensional mapping. So we have a small input space is very small, but it's possible to. Okay, let me explain. Yeah. Oh no, but I don't have pen. Sorry, I don't.
Right.
Oh, okay. And where is the eraser?
You could use the right side of the book. Right side.
Yeah.
This is a simple example. This is a one-dimensional input.
Okay.
And two classes, red and blue. Black. So it is impossible to classify. If we use a single classifier like our model, like this one, it is impossible to solve because even we draw it here, the line, it can be classified this one, red, but this side has both blue, black and red. But so reservoirs using reservoir, it's possible to map high dimensional space. For example, like this.
Okay.
1, 2, 3, 4, 5. Okay, now I put 5 here. Now, as you can see, it's possible to distinguish two. So dynamics.
So any dynamics would help, even if I were to pick Z, XX, some other dynamics.
It's a good question. Actually, if we don't have a rotation, in this case, rotation, if you don't have this one, and if we have only Z-Z interaction, it's impossible because Z-Z interaction is a diagonal.
Sort of an eigenspace, is it?
Yes,
It's not
so
back to itself.
it only change the phases of state, and it cannot, this one, I mean, the dynamic it does not appear in these populations.
And only X. Only
So-
X.
Only X or Y is part of it. That's why we need a small representation here. But later I will show the, please wait a bit. I will show another example, and maybe it helps to answer the question. Okay, now to answer this question, general question, how much compressor needed for reservoir computing to solve the like a more practical problem? For example, image classification. The problem is, for example, image classification, like MNIST, digital images. It has a 28 times 28 pixel, about 800 pixels information, like this. So to encode an images for all pixel information with a single qubit gate, like rotations, it means that it requires many qubits because one single qubit has only 2 variables. Cannot be encoded into NISQ device with few qubit devices. Because in MNIST case, it requires 400 qubits at least. Or, okay, but how about the entangled state? It might be possible to encode all information of pixels using entangled state like this one. So and generally quantum states can be represented by like this. And for example, n is over the 10. It's quite possible to encode this one to C1, C up to C784. But to make this state, it requires many 2-qubit gates. And currently it is challenging due to the noise. That's why image recognition has not yet been implemented considered as an application of NISQ devices. But I want to ask you, do we need all information to classify these images? I don't think so. So that's why we use the PCMR. So we expect our QS can solve the more complex problem, such as image classification. To do that, we complex this information nicely to the smallest size. Compress 784 components into 2 times any principal component efficiently using PCMR. This is a classical data processing approach. And this is very cheap, actually, not so expensive. Now, let me show the result. Demonstration of QRC with MNIST classification. Here I'm showing the results of our MNIST classification for testing, not training. So blue line shows the result of DTC, and the red line is the result of random one. So as you can see, at the critical point, the performance of DTC is comparable to that of CUV, or CUV, the random one. It tells us the performance QRC using natural dynamics has almost same power of that of the random matrix, and it tells us so it can perform on NISQ devices using DTC. And an interesting point of this result shows is is that the performance of 2T-DTC dramatically changed before and after its critical point. Gradually increases and gradually decreases with different rotation error. So it shows us that the dynamic space lines may create some complexity. We also finally, so we also compared our approach and the previous work. So in previous work, MEH classification was performed with 784 cube using the tensor network approach. And they achieved 95.5% accuracy in the testing. Now, in our work, we achieved 97.5% accuracy in the testing with 11 qubits, much smaller than the qubit. If you compare the number of qubits, you see, it's obvious. Our number of qubits much less than their number of qubits. So this is the main message of the future work. So we show that one approach to utilize the complexity of a driven system as a new quantum information processing to solve practical problems, such as image classification. We show that quantum minimal dynamics are as complex as hard random unitary. And this is the future work. So now, before I close my talk, I would like to briefly advertise my colleagues' recent work. This work is done by Aoi. He's a PhD student in the office. Actually, he really wants to come to India, but he's super busy now. So I think he will visit India soon, someday. So he tried to understand that the mechanism we try to understand why reservoir has such a nice power to solve the evidence data by looking at the Hermitian. So any unitary can be represented like this, like a exponential form with some Hermitian matrix. And looking at this Hermitian matrix, it might, because this has some information of unitary. And he shows that it can be mapped to the network structure like this one. The diagonal term represents the nodes and self-compact. And also, of diagonal term is represent links between nodes. And by focus on the distribution of these amplitude, he shows that in his paper, it has some information of the complexity of the reservoir. But sorry, it's his work, so I think he will give the talk the next time. Okay, thank you for your attention. Yeah, please.
Yeah, the question that I have is, I'm struggling to understand when we have a quantum reservoir, which we are not optimizing any of its parameters. So how are we getting a better performance? I understand when you draw that, like instead of a straight line, we have something of this kind. But like you still have to, when you actually prepare the model, you still tweak the error parameter or some parameter in the reservoir to see which gives you the optimal performance, right?
Yes, that's true. Yeah. Actually, we don't have any at the beginning of this project, because we don't have any. We don't know that what kind of reservoir is good. So we want to understand there are some universal class or some properties to the reservoir which has not enough complexity. We try to understand what kind of complexity or property are necessary, and want to understand to see it. We consider the DTC models because by changing the epsilon, they show different dynamics, and it tells us So maybe too chaotic dynamics is not good to you. It's trade-off because it is too regular maybe, but too chaotic. But still it's not clear yet. Yeah.
So, like we optimize the parameters of the classical layer, we are not doing such an optimization for the quantum reservoir, of course, but it's still we do some tweaking of the underlying parameters so that it's in the optimal, at least as far as that quantum system is concerned, right? So what I'm trying to say is, like in a typical deep learning network, we optimize all the weights.
Yes.
Right. Even if it is a quantum deep neural network, we optimize all the weights of the quantum system.
All of the weights.
Here we are not doing anything with the quantum system, which is great. So we just tweak the classical layer, the weights of the classical layer, and the quantum layer. It just lends us with the complexity that is required to like be able to see the straight line as a parabola as you have drawn, for example, here. So that's a great thing, but I'm trying to understand, like still there'll be some tweaking that we would require for the quantum part to be able to gain from its complexity. That's what I'm saying, but it's not going to be as involved as we do in a deep neural network, of course.
Yeah. Thank you. Yeah. That's true. Yes.
The classifier that you have, you finally have to classify the data, the output that you get out of your measurement. The measurement.
I want to understand how the prediction part of like this part. Okay. I don't know. I have a slide. Some slide. Maybe I have a slide to briefly explain. I don't know. Because it's not related to the quantum part. Maybe I don't have it. I like this one. So we have input here and the network, and after softmark, it is normalized, like a summation of these values to be 1, and like this. And we pick up the maximum one. In this case, the 9. If we can have the input is 9, then this part should be returned the maximum number. And this we assume, okay, this result should be 9.
You need at any threshold there, or
no, you don't need any threshold. What do you mean threshold?
Typically, we have the sigmoid function, right?
Yes.
We have a sigmoid function, and we have set thresholds for the classification.
Okay. A bit different from this one because it's a sigmoid functions. We don't use sigmoid, but we use a softmax.
how scalable is this as you go to bigger systems? The classical part, particularly.
Scale of what?
As you increase the system size,
Of quantum system.
as you handle more and more data, how
data.
easy? Yeah, because you're encoding the data, input data, the classical data that you have into a quantum system, right?
Yes.
To the quantum reservoir. What do you call your reservoir?
Sorry, can you explain?
Yeah, go to your first slide, one of your earliest slides.
Okay.
Yeah, this one, the top, the one on the top.
Okay.
So your data is actually the amplitudes there, right?
Oh, sorry.
So you, right. The encoder.
Yeah.
So then you put it into your quantum.
Yes.
It becomes a quantum system.
Yes.
That is okay. But finally, from the quantum system, again, you measure your quantum system.
Yes.
After a certain time period.
Yes.
So the data that you get is now classical. So you'll have to handle a huge classical data, right? That is what gets into the softmax part, the last part, the M layer and the.
Yeah.
So how
we have to do something.
Right. The right side. Yeah. So you do some classical post-processing.
No, you have to run many times and get short. Actually,
short, but then you again have to classify that by putting into your classical classifier, right?
Yes, you have to put the classical classifier.
So is it scalable as you increase the system size? Like you go to more and more bigger and bigger system?
I don't, sorry, I don't understand your question clearly, but
So I
scale
have
of
more
training,
samples.
more sample means training data.
Right, more training data.
Of course, to each training data, like input, we have to calculate the probability distribution,
Right.
but it's independent on this training part.
That's right.
So it doesn't, so you don't need, it doesn't, because it is, okay, this part is not included in the optimization loop, right? So it can be done by once, I mean, one time, yeah. That does not scale with. Of course, if we have many input category, I mean, data size is very large, number of images is very large. We have
Right,
to run
right,
them many
yeah.
times, of course.
Right. That's right. So the thing here is the advantage with your class quantum circuit learning here is that you're getting rid of your
Yeah,
circuit optimization. You
circuit optimization
that is
problem is a bit different because they are
yeah, so you're getting rid of your u of thetas, having to optimize your
to optimize this.
yeah.
The loop, the class quantum part is included in the optimization loop. So each time they have to calculate the probability. That is a bit problem. It means that if you have in our case, QCR quantum reservoir computing, if we have a number of 10 images, then this is 10 times number of shot required. But quantum circuit running takes to number of shot times number of iteration.
Right.
Short need.
Right. And you don't have the barren plateau problems that you have.
Yes, because
You don't have to optimize.
we don't optimize the classical
Right,
part.
right.
Sorry, quantum part. Yes, we don't have a body plateau.
So what are the other kind of problems that you can actually solve by this? So this is what machine learning is also. This is, or how is this related to machine learning?
How it's related to the machine learning?
Roughly, this is what it is. I don't know. That's why.
But our approach, we call it the classical quantum reservoir computing. But it's, as I said, it's similar to the quantum kernel method.
Okay.
We use the quantum part as a kernel to map the input space to high dimensional space.
Right.
That's the relationship between the other machine learning model and our model.
Okay, thank you. Thanks for.
Sorry,
It's a very rudimentary question.
thank you.
So when you're mapping your classical information to quantum bits, you take it say, from your XY coordinate that you have shown, you get theta from there, right? Whatever XY coordinate you take from there, that image as you've shown.
Yeah.
And then you get the theta value from there for each point, right? And then you convert it to the quantum bit, right?
Yes.
But now the question is that if this information is a part of an image, but at some point of the image, the intensity may be very small. And at some point, intensity is very large. How do you translate that into the qubit? The qubit has a magnitude which is 1, all of them. But how do we take care of that, this variation of intensity?
Good question. First, we don't encode the pixel information directly into the quantum qubit. As I explained, because we know that we want to solve that's not cheating, but it's something like cheating. We know that we want to, our input is digital numbers.
Yeah, digital number. Now my question is, say, after 5 you have a 0, right?
Yes, so.
But that 0 you have already converted to a qubit.
Yeah.
But if that 0 has no intensity, but you have converted it to a qubit.
So it can be represented like vectors, like this one, using 784 bases, pixels, good number of pixels, and each pixels can be like fundamental 4. Ah, 1, 0, okay, 0, 1. I don't know. Okay, right one.
0, 0, sir.
Yeah, 0, 0, should be 0, 0, sorry. 0, 0, 0, 1, 1, 0, 1, 1. And it can be right as A0, 0, A0, 1, A1, 0, or A1, 1, something like this. Can be represented in the vector space.
Mhm.
And we use the PCM, as the principal component analysis. It gives us a new basis. And using new basis, it's efficient to
I mean, when it goes like the one that doesn't have any intensity, this amplitude, the expansion coefficient,
Yes.
there is 0 in
Yes.
that case. You have the qubit, but its
Yeah.
coefficient is 0.
coefficient is 0. What do you mean the coefficient is 0?
I mean, in the expansion, you have the qubit and then you have an amplitude on that, right?
Yeah.
But that part goes to 0? No, that in that amplitude is fixed, it's 1.
Mhm.
But when you have something to represent which doesn't have any value there,
Mhm.
like no intensity in that 0,
Mhm.
so that also you are representing with a qubit,
Yes.
right?
But yes, yes, yes.
So how does it get reflected finally into your changing to the quantum bits? And I would say that there's nothing there, but you have already put a quantum bit there.
Nothing.
Yeah, there is nothing there. So if that 0 is not there at all.
But 0 has 0 information. There is no 0 mean nothing. Not
There's nothing is the extreme, but I said the intensity variation.
Intensity value 0 is also information, right?
No, what I mean is that in the image, one point has a high intensity, other point has that 4 there has high intensity, and 6 there has a low intensity. Yeah.
Mm-hmm, mm-hmm.
So when you convert these two to qubit, it's the same sort of qubit, either magnitude 1.
I see. Okay. Maybe I can understand. We normalize it. Before put it in the encoder, actually this part is really difficult to explain in details. Sorry. I mean
It's more of an experimental concept.
yeah, it's very expensive. Well, it's got his experimented. I know. More very good, nice questions and.
So I have taken it to the extreme that intensity low means there's almost nothing that could be there. But he said that this exactly what I mean is the 6 and 4. So when you do the qubit, both qubit have the same amplitude, the magnitude.
No, they don't have the same amplitude. No, of course it reflects the intensity. Yes, amplitude. I think maximum amplitude of one is reflecting the maximum of data set, and lowest one is selected by lowest. Sorry, minimum in this gets 0. Yeah, of course. And tuned, normalize it in the process. Encoder.
So that is when you write the full state of this one. But individually, you are converting each of them to a qubit.
Yes, individually converted, but before in PCA, first we to perform principal component, we use the all information data, training data, and find a nice basis set.
So we are not using just one qubit for each image, right? We are actually using many qubits for
one qubit. Sorry. One images, yes.
what?
One images.
Just one qubit for one image.
No, many qubits for one image. Yes. So to the n components are pick up and encoded into qubit.
It's the pixels that are actually in represented as
A pixel. So there in that image, there may be several pixels, right? But all these pixels, if that doesn't exist there, all these pixels have no value. But if you have a qubit for each of them, each pixel, so how do you handle that? That's the question.
It will fail to classify that. If there is no image, then there will be no output.
Of course.
That's what-
So you have 10 by 10 pixel to represent that 6, that box.
Mhm.
And so you have 10 by 10 qubits there already,
Mhm.
but there is nothing. So its intensity is 0 there.
Then it's what? For example, 9 and 0, all 0, you mean nothing.
But you have taken 9 qubits for that, right?
9 qubits. No. Because my system can encode 2 pixel information. Got 2 angles. So let's see, okay. No, okay, 16 is better then. So this images can be mapped to 8 qubit. Like this part is coded to the single qubit. This part is sent to the one different qubit. If we have 8 qubit, we can encode it. I think 8 qubit 1, 2, 3, 4, 5, 6. Yeah. No. Yeah, why? Okay, anyway. So in my code, I guess 0, intensity 0 means that the amplitude of theta equal to 0, I guess, and 255 is
Now, let me tell you that the expansion that you have I equal to sum over this, right? So if each of them represents a pixel, and if the coefficient C is 0, does it represent what I am saying? That there is no intensity there?
intensity 0 means in binary information it's 0, right? 0. And it mapped to angle 0. Oh, sorry, I don't understand, sorry, clearly your questions. I mean,
He's wondering how you map the.
But when you have a quantum bit, you cannot say it is either 0 or 1, right?
mhm.
So what I'm saying here that in one of the some pixels do not have any intensity,
Mhm.
but you are still converting them and representing them by a qubit.
Mhm.
So now this qubit is neither 0 nor 1, it's both.
Yes,
Right?
it's a position, so yeah.
So a 0 intensity case, you are representing with a qubit. So that means that if I give you something blank and you have represented all of them with qubits, what do I get then finally? So this image is completely blank. All
Completely
pixels are-
black.
all pixels are zero.
Then I think
All pixels are 0.
all 0. This one, you will get this.
So how do you handle that one? You have that many qubits for each of them still?
Every qubit is a 0 state.
Yeah.
And if you have a brightest one, like every has a 1, then you will
So
get.
the qubit is in 0 state, you cannot say, because the qubit is both 0 and 1.
Mhm. You say that the pixels information.
No, until you measure, it's nothing, neither 0 nor 1. But your input is going as a qubit, so you are not measuring anything there. But you cannot say whether it is 0 or 1. It is your input that is going into your calculation, and until you have measured, it's neither 0 nor 1. So this whole qubit, this is going as an input in his calculation. Though no measurement at that point. So this is my question is that how does a 0 image which has no intensity is reflected in the outcome, final outcome?
Final outcome. Well, initial state we want to know. Sorry. Initial state. Our initial state, we want to know the blank or blank, I mean, black images of initial state of black images.
Separate out some data. To separate out your information into two sets of data.
No, if you are using MNIST, there are 10 sets, 0 to 9 possible to get
So here's two classified
into 10
Nine.
classes. 10 classes.
10 classes, 0 to 9.
But I think what he's asking is, what if there is a like image that has nothing in it, like it's just blank?
Mhm.
Then we should also have some class for that.
Yeah, of course,
Yeah.
yeah, but it's common problem in this machine learning. Yeah. I mean,
So that is one of these boxes which is empty. Then the model should be able to classify it into something at the end, right?
yes,
So it also
it's obvious, it's a stupid rejections, yes, because, but unfortunately, because our believe that, I mean, yeah, this model is similar to the other machine learning problem. If we input the images, it is not like yes, it is not images. Then still it predict it looks like 9, 7, or 8, but yeah, but it cannot tell us that it is not image. There's no way. Our reservoir cannot distinguish the kind of input. Yes.
Can come back to this point, but show the kind of
So I guess, correct me if I'm wrong. So the dynamical phase transition is doing the job here.
So
The dynamical phase transition from DTC to this melted DTC is doing the classification here.
yeah,
Yes.
seems like yes.
Yes. So the critical point, does it depends on the noise? This dynamics is Liouvillean or only the Hamiltonian
It's
dynamics?
only the Hamilton dynamics.
But any kind of noise will affect the critical point, and their classification will be affected by that noise. Because you said the classification is best near to the critical point. If you go in the chaotic regime, you cannot classify it well.
Yes.
So this critical point is affected by the noise in the system, or?
No, this is a simulation. And like we consider this calculation only done the classical laptop as a simulation. We assume that our system is a closed system, not open system.
Okay, and suppose this is one kind of system show this kind of transition, but suppose there are kind of a bifurcation kind of thing. So you go from one point to another, and you again come back to that point. So suppose two phases are your DTC and melted DTC, and after some time you are again coming to the DTC phase. So if you approach that regime, then your classification will be affected not by this Hamiltonian. You can engineer other kind of Hamiltonian for that.
Sorry, can you say again?
Suppose you are having two phases here, DTC and melted DTC.
Yes.
So after some point, you are again coming back to your DTC phase. Let's say your dynamics is in such a way.
By changing rotation area, you mean?
Yes.
Yeah, after some point, it come back to the DTC phase because, yeah.
Yes. So about that point, how about the classifications there?
It's the periodic.
So the classification will be means for some time, for some regimes, you can classify the data. For some regime, you cannot classify the data.
Yes.
It will go like this.
Yes.
Okay.
It depends on the value of rotational error. But it's a good question, actually. Yeah. Yeah, of course. So.
This is, I think, regarding the same thing that Professor Dev asked just now. So my question is, let's assume you have an image from your experiment where you have single photon emission sites, and you do an imaging of that single photon emission sites using some microscopy technique. Okay, so you have intensity distribution at each of these boxes. Right, some of those emitters might not be good, so they will not emit maybe single photon, may emit more than single photons at a time. How do you discriminate using your machine learning program which one is good, or where should I do our correlation measurement, or whether it is really single photon? Or I mean, is there any algorithm before doing any measurements on that specific sites whether they are really single photon emitters. Can we specify that?
Why you are talking about single photon emitter? Sorry.
Okay. I think so. My question.
Take the intensity also.
Yeah.
Emitted
So-
1 photon, others was emitted 5 photon.
Fast.
And then I think it also correlates to the place that we have a test for conducting computer with 500 qubits. Right? Some of the qubits are bad.
The experiment
You
point.
want to avoid those in your programming.
Yeah. So
First, right? You want to avoid this in your programming. Similarly, if you want some place it emits 5 photons, it doesn't want that. So you want to exclude that one from it.
Yeah.
Calculate. So whether your machine learning can help in that.
You want, if you mouse in experiment, maybe we have to use, maybe I have need to use some part system, and these are some noise, and as a result, we cannot get this part you are talking about. No, input part.
yeah, input is different. That's what. So in all these boxes, the intensity is not same for all these cases, like Professor Dev mentioned. You might have high intensity in some places, and in few boxes you have less intensity.
So intensity you're talking about is
Or the amplitudes, whatever.
or the images.
In the images.
But first, that's what I don't understand. Sorry. This image is the prepared like a classical informations.
Yes. So in this image, let's say you have 3, and then there is another box. You have something else which has less intensity. So let's say 5 has higher intensity and 0 has less intensity. So from that, can you discriminate whether there is a single photon emission?
We have to normalize it in the classical laptop, of course.
Okay.
Classical data processing helps us to clean the information before, of course. Otherwise, as you said, sometimes in the cameras, we get very dark images. But this is a brush up using classical technique. But it is common in the other.
It's also not the job of this algorithm.
Yes, it's outside of.
Yes, it would be.
Yeah, yes. Yeah, so far. Of course, we can, in the future, maybe we can have to consider. Okay, I now understand. Yeah. Even there's some noise, I think it works, but it depends, of course, noise of type of noise. Epsilon will come. Yeah. Yeah, nice. Yeah.
I think there might be some unitary you need to encounter this loss of photons, maybe in terms of, I don't know. So basically there is photon loss, which is happening in case of single photon or multiple photons. So that's my guess.
I think unitary part doesn't have a power to distinguish which is noise, and because they don't train the unitary part. But it might be possible to create some competition to single part the model to be noise. Sorry.
Speaking.
Yeah.
Okay, I'm okay. Thank you.
Oh, thank you.
Are there any online questions?
Yeah, maybe just a simple one. So, so in MNIST data, as you mentioned that you could achieve almost state of the art with only around 11 qubits. Yep. And MNIST pictures, as we know, it's 32 by 32 pixels. So if instead of MNIST, supposing you had to go into ImageNet, where you have 128 by 128 pixels for one image, do you have some idea about how many qubits would be required to achieve, a similar kind of good performance?
I mean, different data set, not image.
Yeah, different data set. Like suppose instead of 32 by 32 images, you have,
Yeah,
something bigger. So
bigger. Yeah, it's a good question. Actually, because maybe you know that MNIST is not so difficult compared to other classifications.
true, yeah.
Like a first MNIST is the next interesting data set for us because still it's simple, but compared to MNIST, the first one MNIST is much complex than the MNIST. And of course, in first feminist case, we cannot get very nice result in the 11 qubit case. So I think it depends on the problem of task and also like a color images because they have the 3 filters. I mean RGB, red, green, blues, and it's for each colors we need we have to prepare the qubits for each sector, I mean each colors, and maybe 3 times bigger than the MNIST case, maybe. Like
so, I mean, how does the trend vary? Like, do you think if, suppose, I mean, I'm trying to figure out, say, from 32 by 32, if it goes to, say, 100 by 100, almost 3 times, let's say. So if the width gets scaled by 3 and the height also gets scaled by 3 of each individual image, would you get a good idea of how many more qubits you would need? Would it be 9 times more qubits or would it be 3 times more qubits? I mean, how would it go? Square, linear, some idea?
Sorry, 100 times 100 means the number of pixels, you mean?
Yeah. Sorry. Yeah. I'm sorry. Yeah.
Okay. That case is possible too. I mean, I think it doesn't. I think, of course, we need some more qubit. Oh, why it doesn't work? But okay. But as you said, we already give up to implement all information of pixels. And that I explained in the encoder part. Okay. Okay, this is the last slide. Okay. This one. Here. So we have 784 pixels in MNIST, but we only to pick up 2 times n, like even case.
True. Yeah.
And I don't think it scales with number of pixels. Even we have 100 times 100 pixels. Because for classification task, I believe we don't need the full image or information of images. Most of parties are not necessary.
Oh, I see. So you're saying that, so it won't change much. Like, I mean, even with 11 qubits, you would be able to do even.
Yeah, it might be possible. Of course, as the images sizes increases, more information is they have more structures. Images has more structures. It might be necessary to increase the number of qubits or pixels information we have to put. But it doesn't mean that like a scale with sound does not scale. I think does not scale with pixels. I mean the size of the images, because
Okay, yeah, that's all I had. Thanks.
Thank you.
Okay, I think we have time for one more question.
No. Okay.
Okay, so if there are no questions, I mean, let's thank Dr. Sakurai again.